Hello, good morning, student. I hope you all are very happy, healthy, and fine at home. What did we discuss yesterday? We discussed about the experimental proof for the inversion of configuration. We are discussing about the stereochemistry for SN2 reaction, and SN2 reaction there is a inversion, so that inversion we are giving some of the experimental proof for the, and in the previous case we have given experimental proof for the inversion of configuration. Now the second example, what we said in the previous example, we consider as a chiral substrate treated with that sodium hydroxide, resulting into its what we can call it as the starting substrate has R configuration. When we got the product has S configuration. That experimentally proved that in SN2 reaction there is a inversion takes place. But if you look at the starting compound is a different one and the product form is a different one. Therefore, there may be optical rotation is different. For now, we are considering here experimental evidence. Evidence is nothing but as a proof for inversion of configuration. What here we are considering the chiral center, starting with the chiral center, and as we know that chiral carbon or chiral substrate means which is optically active in nature, because the chiral center or the chiral carbon which carries 4 different group, that carbon is known as a chiral carbon or the asymmetric carbon atom. And now here in the previous case we have taken as an example of R minus 2 bromo octane treated with sodium hydroxide that produces or that gives the 2-octanol. Here we are going to consider the different example. The example is, I think, R1-phenyl ethyl chloride treated with some tosyl chloride forms some of the intermediate, and that is treated with the sodium acetate, and that further treated with sodium hydroxide, and then that gives the product. Let us see first one. Here we are going to consider the example of R1-phenyl ethyl chloride, 1-phenyl ethyl chloride or ethyl bromide, we can call it ethyl chloride or the ethyl bromide. It doesn't not there. We are going to take as a 1-phenyl ethanol, 1-phenyl 2-propanol, 1-phenyl not 2-propanol. I think R1-phenyl 2-propanol. So that is the example we are going to consider here, R1-phenyl 2-propanol. Now, can you draw the structure of first 2-phenyl 2-propanol? Prop indicate as a 3 carbon atom in the straight chain, right? At 2 position, these 2 indicate as a position of OL mean alcoholic group, and if you start from this side or this type, let us see numbering from 1, 2, 3. In this position, phenyl group means you can draw here pH, or this pH is nothing but we can call it as C6H5, this, or we can draw this the phenyl group like this. These are the various, remember this one, right? pH is nothing but, in short, we can write C6H5, or you can show that benzene ring, and that is. Look at here now, at one carbon atom there is a 2 bond. How many hydrogen atom I should attach here? CH2, right? Here 1, 2, 3 bond already there, one hydrogen atom, and this terminal carbon there is only one bond, so I should attach 3 hydrogen atom. So this is the structure of 1 phenyl 2 propanol. Now again draw in terms of this R, and as we know that, let us see here carbon atom and this OH, one methyl group which I am writing here, this one CH3. Look at here, methyl group, carbon atom and OH, they are lying in the same plane, and that's why I am showing this by normal lines. Now this is only one chiral center atom is present in this molecule, and one of the hydrogen atom I am showing like this over here, and now this is a phenyl group, this the phenyl group, so you can write here pH, right? This is a phenyl group. Not phenyl here, I think there CH2 is remaining there, right? Here is a CH2, then pH, right? This group CH2 pH, right? Here CH3, this is a chiral carbon shown by star over here, OH CH2 pH. This is a structure of, now whether it is R or S, again give the priority number. Look at here, oxygen atom, it will get the first priority, then carbon atom, and this carbon atom, which carbon atom has then go for the next atom. Next atom, here is a carbon, here are the 3 hydrogen atom, therefore it will get the second priority, ultimately this will get the third priority, and this one is the last. Only think about 1, 2, 3. Remember, while showing as a RRS configuration, rotation, so start from 1, 2, 2, 2 to 3, that is a R configuration, and therefore it is a R 1 phenyl R 1 phenyl 2 propanol. So this is a first. Now here this compound is treated with tosyl chloride, TSCl. This is known as a tosyl chloride, TSCl. Tosyl chloride is nothing but as a para-toluene sulfonyl chloride. Here the structure of tosyl chloride, let me draw here the structure of, this is called as a tosyl chloride. The structure of tosyl chloride is this one. This here is a CH3 group, then S double bond O Cl. This part is known as a TS, tosyl group, TS and Cl. This is a tosyl group, or it is known as a para-toluene sulfonyl chloride. The name of this compound is a para-toluene sulfonyl chloride, or this is known as a tosyl chloride. This is known as a tosyl chloride. This is known as a tosyl chloride. So here what is going to happen? Now here OH group is a bad leaving group, as we know that, and we are converting it into still better leaving group. What we are doing, the lone pair which is present on the nitrogen atom, this is the first step. in the first step what is happening, the lone pair which is present on the oxygen atom directly attacking on that tosyl group, there is a departure of chlorine, one hydrogen from here and one Cl from here, there is a fumes of HCl that goes in the atmosphere, and you are going to get here the compound is this one, this OTS, I am in short writing, and then this is a CH-3, then hydrogen atom which is as it is, and then this CH2 group, this CH2 group also as it is, CH2 and pH, right? CH2 pH, the chiral center remains as it is, right? Now what is going to happen in the second step, that is a SN2 reaction. Here I am treating with the weak nucleophile like this one, CH3, C double bond O Na. There is a negative charge, positive charge. This is called as a sodium acetate. This CH3, C double bond O Na is known as a sodium acetate. Sodium acetate. The name of this compound is a sodium acetate. It is a very weak nucleophile, and as we know that this SN2 reaction, the nucleophile approaches from the backside. So this nucleophile attacking from the backside, the tosyl group is a good living group, and it get departed over here, and you are going to get the product, this one. Then here the methyl group which is over here, then hydrogen atom dotted, and then this is a CH2 and pH, and now here O, and then C double bond O and CH3. Now here what is happening, if you look at carefully, the attack of nucleophile from the backside, and the bond is breaking, bond making and breaking takes place at the chiral center. In the first step there is no bonding, breaking or forming takes place in the first step. So breaking of bond is not at a chiral center in a first step. Only we are converting here the bad living group. OH is called as a bad living group. We are converting that bad living group into as a good living group. Now here the living group is departed here, O minus OTS, right? OTS is nothing but, I am showing here that tosyl group O minus, right? Then S double bond O, and this group, and now this group CH3, this group is well stabilized due to the resonance. You can, as we know that the resonating structure C double bond O, S O minus double bond O, and this structure is as it is, CH3, right? And this why it is a good living group, because that good living group is well stabilized due to the S double bond O resonance effect, and that's why this one is a good living, why it is a excellent good living group, well stabilized due to the resonance that is there. Now in the third step, what is happening, there is a hydrolysis. In the third step, hydrolysis with that sodium hydroxide, this is a hydrolysis process. What is going to happen, this nucleophile now is going to attack on this carbonyl group, this double bond revolving as it is, and it will take the solvent from the water, and the resulting product you are going to get here HO, then C, this methyl group here, then this hydrogen atom, and this CH2 and pH. If you put the mirror over here, what do you see? They are enantiomers of each other. Enantiomer means what? Everything is the same. Physical properties as well as chemical property of those compound is the same. Only they differ by its rotation. One is rotating the plane of polarization to right hand side, another rotate the plane of polarization to the left hand side. Means opposite rotation, opposite equal but opposite rotations are there. Means if you see this is a substrate which is a chiral substrate, and if you put here is a mirror. In the last second chapter we have learned how that mirror images or enantiomer is called as. Enantiomer means what? They are non-superimposable mirror images are known as enantiomers, and only their rotation are equal but opposite in nature. Look at our two hands. They are enantiomers of each other, means they are the non-superimposable mirror images of each other. If you draw this structure like this, here methyl group, then this OH, then this is the hydrogen atom, and then this one CH-2PH. And now you put the mirror over here, and what do you see? It's a mirror image. Then see, here is a CH-3 dot hydrogen atom, and then this one is a CH-2PH, right? CH-2PH means exactly mirror images of each other. This first one, and then remember this is a R. Now what will be the name of this compound? The name of this compound should be, this is a 1, 2 and 3. What is this? This is a S configuration. Yes, 1 phenyl, 2 propanol, 2 propanol, 1 phenyl, 2 propanol. Means they are, this having as a R configuration, this must have a S configuration, and therefore they are enantiomers, means non-superimposable mirror images of each other. And if experimentally they have given the specific rotation alpha is shows as I think plus 33 degrees centigrade, whereas this shows the alpha is found to be minus 33 degrees centigrade. It's enantiomer, and therefore in this way this is what we can call it as a proved, or this is the evidence. The 5-mark question may appear in an exam like this. What is SN2 reaction? Give the evidence for SN2 reaction. So this is one of the best example to prove the inversion of configuration. Starting with the chiral center, if your substrate has a S configuration, your product should be R configuration. If your substrate has a R configuration, your product should be obtained in a S configuration. So that is the meaning of that, the inversion, and that prove that there is a inversion takes place. Means they are completely inverted product. Therefore SN2 reaction is there is a inversion product is obtained. So I think with this we have seen second evidence for the inversion of configuration. I think with this let us stop today here. Remaining we will see the next lecture. Thank you. Have a nice day.